This is your presenter, Asloob Mudassar, and I am presenting slide number 16B of the course on atomic and molecular physics. In the today's lecture, I shall be covering emission line spectra as characteristic radiation. And this is the second lecture of the series on X-ray spectra. So this lecture must be studied with the previous lecture, which is given in slide number 16A. So let's discuss emission line spectra, characteristic radiation. Figure on page number 5, which was related to the previous lecture, and I am also going to show you this figure again. The figure on page number 5 shows characteristic radiation, which consists of a relatively small number of lines. So you see that the figure I am going to show you consists of small number of lines. The lines are grouped into series which converge to a short wavelength limit called an edge. So this word short wavelength limit, which we call an edge, this will be explained not only through page number 5 but also through other figures which will be given in the today's lecture. So let's discuss the figure on page number 5, which I have used as an appendix. So this is figure 5 from the previous lecture. And you see that we are plotting the spectra of the X-ray radiation. You can see that the Bremsstrahlung spectrum is a continuous spectrum. And for these three different types of energies, these spectra has been shown. That is for 40 kV potential difference, for a 31.8 kV potential difference, and for a potential of 23.2 kV. These are the potential differences which were applied to accelerate the electrons to obtain these spectra. And you know that if you want to obtain the energy of an electron, you can say that the energy of electron corresponding to the first plot is a 40 kilo electron volt. And the energy of the electron in the second plot is 31.8 kilo electron volt, and the energy corresponding to the third plot is 23.2 kilo electron volt. And you see that the Bremsstrahlung spectrum is shown as a continuous curve. And on top of that one, we have some line spectra, characteristics of line spectra. For example, I want to discuss RH alpha, RH beta, RH gamma, and RH delta and other higher frequency term series are not shown because of the poor resolution of this figure. Similarly, for the second, and you can also see for this first curve Ru alpha, Ru beta, and so on, Ru gamma, and then Ru delta. Ru gamma and Ru delta are not shown in this plot because of the poor resolution of this plot. But you can see that we have two peaks. One corresponds to ruthenium, rhodium, which are RH alpha, RH beta, RH gamma, and the other corresponds to ruthenium, which is Ru alpha, Ru beta, and so on. So these are the characteristic lines, and because our anode is actually made up of two materials. One is the ruthenium, and the other was the ruthenium. And the ruthenium was used as a smaller concentration material was the ruthenium, and the major concentration was the ruthenium. So we have Ru alpha. So actually rhodium. So Ru stands, RH is the rhodium. So RH is from the rhodium. RH alpha rhodium. RH beta again corresponds to rhodium. RH gamma again corresponds to rhodium. And Ru alpha corresponds to ruthenium, and Ru beta also corresponds to ruthenium. Actually, RH alpha, RH beta, RH gamma, and RH delta, and so on, this forms a series of characteristic lines. Similarly, Ru alpha, Ru beta, Ru gamma, and so Ru gamma, and then Ru delta, and so on. This will form a series of lines corresponding to the ruthenium. So RH alpha, RH beta, RH gamma, RH delta, and so on. This is a series of characteristic radiations, and this corresponds to the rhodium because our anode is mainly composed of the rhodium, and then of course some small concentration of the ruthenium atoms are there. And these are the characteristics. You see that RH alpha has the highest peak, then RH beta, then RH gamma has a smaller peak. So the highest peak is RH alpha, then RH beta has a slightly lower peak, RH gamma then has even lower peaks, and then RH delta and so on. So you see that the peaks becomes lower and lower in intensity as we move on to the higher orders of series. And then ultimately, the last point of the series will be called as the edge of the series. So which we call here, for example, if we are talking about K series, then it is called K edge. If we are talking about M series, it is called M edge. So similarly, you see that all these series will have the edge. And the edge means that the corresponding wavelength corresponding to that edge is the minimum wavelength or the highest energy, because frequency and the wavelength are reciprocal to each other. So when last series element has the smallest peak, smallest wavelength, it means that the corresponding frequency or the corresponding energy or the energy corresponding to that peak will be the maximum energy. So you see that then we talk about when we keep on going on, when we keep on discussing this series, that is RH alpha, RH beta, RH gamma, RH delta, and so on. Then of course it means that we are talking about this series, and ultimately the last element of this series, which we call as the edge of the series, will give you a corresponding wavelength which is the smallest among all the series elements or highest in energy. Similarly, you see that for the red curve, which is shown for the energy of the electron with the 31.8 kilo electron volt energy, give you a Bremsstrahlung spectrum shown in red, and of course there are also some peaks which are shown with the arrows point, means that these peaks are moving forward in the upward direction, and of course similarly we shall have many peaks corresponding to that one, but relatively smaller number of peaks in comparison with the energy of the electron with the spectrum obtained with the energy of electron of the order of 40 kilo electron volt. So 31.8 kilo electron volt energy will have a lower number of peaks, and similarly you can see that in the spectrum corresponding to 23.2 kilo electron volt there are no peaks shown. So if we have used over here the electron energy corresponding to, for example, 100 kilo electron volt energy of the electron, the corresponding spectra will then contains RH alpha, RH beta, RH gamma, RH delta, and so on. So more spectral series, so more elements of the series will then be evident with greater energy of the electron, which are accelerated towards the anode. So the ultimately edge, the edge means that the values of the peaks corresponding to the highest energy. Of course, that will be smaller in intensity, but that will have the greatest energy, and that is called the edge of this series. I shall also be talking about these edges in more detail. So let me read this statement, paragraph 5, this paragraph again, that the figure on page number 5, which I have just discussed, shows characteristic radiation which consists of a relatively small number of lines. For example, as you have seen that the number of lines for RH alpha, RH beta, RH gamma, and RH delta has very diminishing values. Similarly, RU alpha, RU beta, and so on. So these were the few in numbers because the energy of the electrons were not very high. The maximum energy in those spectra was of the order of 40 kilo electron volt. But if we have used the spectrum, if we have plotted the spectrum with the electron energy of the order of, for example, 100 kilo electron volt, then you would see that many more lines will be evident. The lines are grouped into series which converge to shorter wavelength limit. For example, RH alpha has the highest wavelength. Then RH beta has a slightly lower wavelength. Then RH gamma has even slightly lower wavelength. And if you keep on proceeding towards this, and you will see that the last line will have the shortest wavelength, and that is called the short wavelength limit, and also known as the edge of the spectrum, edge of the series. So the edge of the series will have the highest energy, will correspond to the highest energy in the spectrum, that is correspond to the shortest possible wavelength. When rhodium anode, with the rhodium anode, you see that I discussed the figure on page number 5 with the anode made up mainly of rhodium, with the limiting value of with the minority of the contribution was due to ruthenium. So with the rhodium anode, the following lines and the series were observed. For example, if you applied an accelerating voltage of the order of greater than 0.5 kilovolt, you will see that only M lines will be observed. Lines of the M series will be observed. And if the electrons are accelerated through a potential of voltage greater than 3 kV, then of course the lines of L series will be observed. And if the accelerating voltage for which the electrons are accelerated is greater than 23 kilovolt, then of course lines of K series will be observed. The lines of K series are doublet. Optical spectra allows a large number of lines which depends on the nuclear charge Z and the chemical bonding in a complex way. So these are the two parameters. One is the nuclear charge Z and the other is the chemical bonding, which in a complex way. And these are the two parameters which determine the optical spectra, and the large number of lines will depend upon these two parameters. There is a limited, and this will be explained through a plot which I am going to show you in the next page. There is a limited number of observed lines which can be grouped into a few series and shown on the next page. For example, this on this page, and I am coming back to this page to explain this spectrum. The spin orbit coupling increases with Z. That is, the spin orbit coupling is a function of Z. And so L1, L2, L3 diverge out. Here you can see that the lines in the middle, for example, these lines, which were almost a single line at the start, then you see that they will start diverging out with the increasing value of Z, and the Z is plotted along the horizontal axis. So as Z increase, then for different materials, you will see that the lines are going to diverge. I am talking about the L1, L2, and L3 lines, and you see that ultimately these were diverge out well, and you can easily discriminate between L1, L2, and L3. And you see that when these lines are well separated, and you see that these have reached to their edges, because the values of the Z value, that is the value of the nuclear charge, is maximum at these values. So these values of L1, L2, and L3 has reached their edges. So L1 and L2, L3 have reached their edges, and you see that these are the edges. That is the corresponding to these edges, the wavelength will be minimum. And we have also resolved these L1, L2, and L3 lines, because with the increasing value of Z, the LS coupling between the orbital spin magnetic moment and the orbital spin magnetic moment and the spin magnetic moment will increase with the value of Z, and due to that one, splitting will increase. So L1, L2, and L3 can easily be discriminated. The spin orbit coupling increases with Z, and so L1, L2, L3 diverge out. Corresponding lines and edges are found at increasing quantum energies as Z increases. The different series are designated by K, L, M, and N, and so on. So K series, L series, M series, and N series. So let me you first of all explain this one. You see that on the horizontal axis we have the nuclear charge plotted along the horizontal axis. It means that the heavier atoms are shown on the are shown for larger value of Z, that is are shown on the right hand side, and the lighter items are shown on the left hand side where the value of the Z is very small, for example 0 to 10. And on the vertical axis I have plotted the frequency divided by the that is the square root of the frequency divided by the Rydberg constant. So this parameter has been plotted along the vertical side, and you see that its value increases from 0 to about 38 values. Then you see that I have plotted the different values of the series. That is, I have plotted K series, I have plotted L series, I have plotted M series, and then I have plotted N series, and then ultimately I have plotted the O series. So you see that the K series begins with very small number of Z values. And you see that even if you increase the value of Z, the K series remain as a single line, that is the unsplit lines. Because for very large values of Z, then of course ultimately we shall reach at a point when the K series will split into two, for example, into two lines. But that will be for the value of Z much greater than the value of Z shown in this plot. So for the value of Z up to 90 degree, we should see, and for the you see that K series has been plotted for the values of Z up to 40, because I have not plotted the other values of K, because then the plot will be very large and it's difficult to show such a plot. So you see that if you increase, if you plot this K series for larger values of Z, which I have not shown, then you would see that K line will also split into more lines, for example, into two lines at least. So the K series will split into two lines, that is K alpha and K beta. And even for higher values of Z, you will see that the K series will split into K alpha, K beta, K gamma, and K delta, and so on. So this will be the K series which will split into more number of lines as the value of Z is increased, and for those values of Z, the K series is plotted. Now I am moving next to the L series. So you see that for the L series, we have plotted all the 90 degree or up to the Z is equal to 90 degree. And you will see that in the beginning, the L series was converged almost to a single line. For example, in the very beginning of the Z values, almost all the three lines are converging out at a very small value of Z. But if you increase the value of Z, then of course the LS coupling, that is the spin orbit coupling, will increase for the L series, and you will notice that the splitting will start, and the splitting will become dominant when the value of Z is beyond the value of 50. Then of course you can see that these values are well separated from each other, that is L1, L2, and L3, which are the three lines of the L series, are well separated, and when you reach their final values, these are called the edges of the series. So at the last point, when Z value is very high, you may regard L1, L2, and L3 as the edges of the series, as the edges of the L1 series, edge of the L2 series, and edge of the L3 series. Similarly, you see that at the third series I am plotting is the M series. So M series also, you see that for very small values of Z, they will initiate from the same value or from the same point, and then of course they will start diverging out. So the M series diverges out into M1 series, M2 series, M3, M4, M5, and so on. And you see that for large values of Z, for example, at 90 degree, these series lines are well separated from each other, and you may consider these as the edges of the series also. So M1 edge, M2 edge, M3 edge, M4 edge, and M5 edge. These have been shown in different colors and have been also marked with the different colors so that you can identify them. Similarly, I have the N series. And you see that a similar pattern is also shown for the n series, which split out and diverge out for larger values of z. And you can see there I have n1, n2, n3, n4, n5, n6, and n7. These 7 lines of the n series have been shown, and at the end you can see that these are the edges of the corresponding series. Then you see that I have at the end plotted O series. So O1, O2, O3, O5, and O5, O4, and O5 series have been shown. And of course, I need to plot further beyond the value of Z so that these can be well separated, and you can also label them separately. Here at the moment, you can separate out I1 from the other parts of the series because I2 and I3 represent almost the same series, unconverged series. Similarly, O4 and O5 are also undiverged and overlapping each other. So for greater value of Z, we shall see that which I am not plotting over here, but you will ultimately see that these O1, O2, O3, O4, and O5 will also diverge out, and you can discriminate between these lines and also their corresponding edges. So this is what I have explained this spectrum. Now let me read the corresponding theory that I have written over here. This is also may be referred to as the Moseley diagram of the absorption edges, because these have been observed using the absorption spectrum. For edge frequency nu, that is if you want to calculate the edge frequency nu, and similarly you can, when the frequency nu is known, you can also calculate the corresponding wavelength, which will be the limiting wavelength corresponding to the edges. So the wavelength corresponding to the edges may be referred to as the limiting wavelengths. Now for edge frequency nu, this formula is applicable. That is the square root of nu over Rydberg constant R is equal to Z minus S over N, where S is the screening number. Screening number is what we have discussed in the first lecture of this series. And the principal quantum number and the screening parameter S are different for different shells. Moseley lines are not parallel and diverge out as Z increases, because spin orbit coupling increases with Z value 2. So due to that one, the lines are not parallel and they are diverging out with the value of Z. So you see that here I have shown that what is the behavior of the K series, L series, M series, N series, and O series when the value of Z is increasing. When the value of Z increases, and as a function, and these have been plotted as a function of the square root of frequency nu divided by the Rydberg constant R. So it is evident that with the increase in the value of Z, the LS coupling increases, and this is the LS coupling that helps to diverge out these lines. The fine structure splitting of the lines. You know that this is the fine structure splitting. This is the fine structure splitting of the lines because this depends upon the LS coupling, that is the spin orbit coupling, and the spin orbit coupling is also referred to as the fine structure coupling. The fine structure splitting of the lines is indicated by the numbers written as subscripts. For example, L1, L2, L3, etc. The K alpha line and the L alpha line can be described for different atoms as follows. So you see that K alpha line and K and L alpha line can be described for different atoms as follow. For different atoms mean different value of Z. And you see that here nu bar, that is the wave number for K alpha lines for different atoms is equal to 3 over 4 into R, that is the Rydberg constant, into the square of Z minus 1. So this can be written as R into square of Z minus 1 multiplied by the parenthesis containing 1 over 1 square minus 1 over 2 square. So you see that for the K alpha line, all the transitions from the higher orders will take place to the lowest order, which is a base order, which is the base line corresponding to n is equal to 1. So for the K alpha line, the transition from the level 2 to level 1 will take place. Now for the L alpha line, the wave number nu bar is given by 5 over 36 times Rydberg constant times z minus 7.4 whole squared is equal to r into z into the square of z minus 7.4 multiplied by 1 over 2 square minus 1 over 3 square. So you see that the alpha line, L alpha line is obtained when the transition takes place from the level 3 to the level number 2. So this is the K alpha line. This is the L alpha line. The other lines will be K beta, K gamma, and so on, for which I have not shown the formula, and you can modify this formula by yourself looking at these two formulas. In 1913, Moseley discovered a linear relationship between the square root of a frequency and Z. Comparing the above two equations with the Balmer formulas for hydrogen, for the K alpha line, the nuclear charge is screened by 1 unit of charge, while the L alpha line is screened by almost 8 units of charge. So you see that here I have converted 7.4 to nearly 8 units of charge. So you see that K alpha line is screened by 1 unit of charge, whereas the L alpha line is screened by nearly 8 units of charge, which is obvious from these two formulas. Chemical bonding has a minor influence on its X-ray spectrum. Exact measurement of this effect provides important information about the behavior of electrons in chemical bonds, which I am not discussing in this course. X-ray emission not only is described by bombarding the anode, which we may call as anticathode with the electrons, but also by the irradiation of atoms, molecules, or solids with the X-rays. This is called X-ray fluorescence. So you see that X-ray emission can be observed if you bombard a node with high energy electrons. The second option is that you eliminate the sample, gaseous sample of the substances, for example, with X-rays, and then of course you can observe the emission of X-rays from those materials. This is called the X-ray fluorescence. Now you see that before I discuss this figure, let me read this paragraph first. An electron hole. Electron hole means that the electron has been removed from a place and a hole is created, which we refer to as the electron hole. An electron hole is formed by ionization of an inner shell electron indicated by an outward pointing arrow. For example, here you can see that this large arrow, which is pointing outward to this dotted orbit, indicates that one electron from the K orbit has been ionized. That is, has been removed from the atom. An electron hole is formed by ionization of an inner shell electron indicated by an outward pointing arrow shown in the figure, which I am including over here in the figure. This is filled by that is the hole vacancy is filled by an electron from a shell which is further out. The binding energies are emitted as X-ray quanta indicated by inward pointing arrows. So let me show you now, let me explain this. So you see that we have ionized a K shell electron. And this arrow indicates that the electron has been ionized and removed from the atom. Now you see that what will happen, a hole vacancy is created. This hole vacancy will be filled by the electrons in the surrounding orbits. For example, this K or this electron in the K hole, that is the hole vacancy in the K shell will be filled either by the electron from this orbit, which and the electron when jumps to the k shell towards the hole which has the higher binding energy, then of course of an X-ray spectra, an X-ray quanta of energy h nu k alpha will be eliminated. And if the electron, so you see that here the electrons is filled by an L shell, then you see that there is also a possibility that the electron will be, that the whole vacancy in the K shell will be filled by the electron from the M shell, and that M shell is shown in red. So the electron you see that has been shown is moving from the M shell to the K shell, and of course due to this difference of binding energy, a quantum of a photon of quanta with energy h nu k beta will be released. There is a third possibility has been shown that an electron from the N shell, which is shown in blue, will move towards the K shell to fill the vacancy of the hole, and then of course a quanta of energy due to a difference of binding energies equal to h nu k gamma will be released. So you see that similarly, if the transitions of the electrons from the higher levels to this K level will takes place, then of course the other the other quanta of photons will also be released, which will be the next quanta of photon of the K series will be h nu k gamma, h nu k delta, and so on. So a series of transitions to fill the K shell, K hole valence electron will be K alpha, K h nu K alpha, h nu K beta, h nu K gamma, and h nu K delta, and so on. This whole series will take place. And this whole series will not take place by the bombardment of only a single electron. So you see that many electrons are coming, many holes are being created in the K shells by the many electrons, and of course many electrons are jumping from the outer shells to fill the vacancy of the K shell hole. To fill this vacancy, many of the transitions can take place. For example, the electron from the L shell, the electron from the M shell, the electron from the N shell, the electron from the O shell, etc. will jump towards to fill the valency of the K hole to fill the valency of the hole in the K shell, and then of course a whole series of K series will be observed, which we refer to as the K alpha, K beta, K gamma, K delta, and so on. Now suppose that we have created so you see that this is the picture when a hole is created, that is an electron from the K shell is ionized and a hole is created in the K shell, and the surrounding electrons in the surrounding orbits will jump to fill the vacancy of the K to fill the vacancy of the K hole in the shell, and then of course transitions may correspond to K alpha, K beta, K gamma, K delta, and so on. Now suppose that you have removed an electron from the L shell. That is, an L electron has been ionized. Then what will happen? The electrons from the surrounding orbit, it means that a whole vacancy is created in the L shell. To fill that vacancy, the electron from the M shell, the electrons from the N shell, the electrons from the O shell, and even the electrons from the higher shell will move towards the L shell to fill the vacancy. And then, of course, the transitions will take place by the electrons, and the quanta of photons that will be released in this process will be M alpha, M beta, M gamma, and M delta, etc. So an M series is formed. So the M series is only formed. Sorry, I have made a mistake. That is this is the M series, and M series is formed when an electron from the M series from the M shell is removed. That is, an electron from the M series is ionized. Then a hole vacancy is created in the M shell, and then to fill that vacancy, or electrons from the outer shells will come to fill this vacancy, then of course M alpha, M beta, and M gamma series will the transitions will take place, and M series will be created or will be generated. Now I am coming out towards the series which is the L series. In the if you want to consider the L series is only generated or formed when an electron from the L shell is removed. The L shell is shown in green, and the transition, the other electrons from the surrounding shells will make the transitions or will make the jumps to the L shells to fill the vacancy. And as a result, the quanta of light H nu L alpha, H nu L beta, H nu L gamma will be created. And even H nu delta and so on. This whole series will be created. And you see that the quanta and the arrows of the electrons which I have shown for this L series is shown as H nu L alpha, H nu L beta, H nu L gamma. So this is referred to as the L series, simply written as L alpha, L beta, and L gamma. So you see that in this picture I have shown you three series. K series will occur only when a hole where a vacancy is created in the K shell, when one of the electron in the K shell is removed and a hole vacancy is created. And the L shell and the L series is created when an L electron from the L shell is removed or ionized, and the electrons in the correspond in the outermost in the surrounding shells will come to fill this vacancy. And similarly, M shell is created or M series is created when an electron from the M series is removed or ionized, and the electrons in the surrounding orbits will come to fill this vacancy as indicated by these black arrows. So you see that I have shown these three series, K series, L series, and M series. So many other series can also be possible. But the most frequent will be the K series, L series, and M series, depending upon the energies which are used to remove the electrons. Either the electrons are removed from the K shells, from the L shells, or from the M shells, or from the N shells. And of course, the corresponding series will be generated when the electrons move from the surrounding orbits to fill the vacancy of the hole. And due to the difference of binding energy, the X-ray quanta are released. And for the K series, the X-ray quanta will be H nu K alpha, H nu K beta, H nu K gamma, and so on. And for the L series, the X-ray quanta will be H nu L alpha, H nu L beta, H nu L gamma. And for the M series, the X-ray photon, the X-ray quanta will consist of H nu M alpha, H nu M beta, H nu M gamma, and so on. So you see that in this way, a series of K series, L series, and M series can be generated from out of the X-ray spectra. And you know that this is not generated by a single electron, but a large number of electron beams are incident, for example, on the anode material. And then, of course, this process occurs due to varying value of the energy of the electrons in the electron beam. Different electrons from the different shells of the electrons will be ionized. That is, the electrons from the K shell, from the L shell, and from the M shell, for example, are ionized, and the corresponding vacancies are created, and of course the corresponding series are generated. Now you see that with reference to this figure, the electron, you see that here the electrons are jumping from the surrounding orbits. For example, for the K series, the electrons are jumping from the L series, from the M series, from the L shell, from the M shell, from the N shell, from the O shell, etc. For example, if the electron jumps from a very outer shell, for example, very close to the, for example, for the valence electron, if that is jumping, then that will give you the K edge. That is, the electron is jumping from the outermost shell of the atom. Such will give you the K series, will give you the K edge. K edge means that the electron has jumped from a very far away shell, maybe close to the valence shell, or maybe the electron from the valence shell is jumping towards the K shell to fill the whole vacancy, and then such a photon emitted due to the difference of binding energies will be very energetic, and that most energetic photon will form the K edge of the series. That is the last edge of the series. That is the last quantum of the K series, and will be most powerful. And that will also will generate you the wavelength limit. Limiting wavelength will be generated, because when the electron is jumping, for example, if the valence electron is jumping, the photon of energy, the photon of the X-ray photon will have the strongest value of energy, which we here call the K edge electron, the K edge quantum of X-rays will be most powerful. And you know that when the frequency is very high, the wavelength, the corresponding wavelength will be very small, which we refer as the wavelength limit. So you see that here I am plotting different edges. For example, 3 elements of each edges have been plotted in this diagram. You see that this is the limit where the atoms are ionized. That is n goes to infinity. Here in this region, in this shaded region, the electrons are removed from the atom, or the ionized, or the atoms have been ionized and the electrons are thrown away. And the ionization energy for different levels is indicated by these thick arrows. For example, these thick black arrows indicate that an electron from the K shell has been removed. And this blue arrow, stronger arrow, upward arrow, indicates that an electron from the L shell has been removed. And this red arrow starting from the n is equal to 3 indicates that an electron from the M shell has been removed. So you see that here again I am going to show only you the 3 series, that is the K series, the L series, and the M series. So the first element of this series for the K series is K alpha, which is due to the transition when the electron jumps from the L shell to fill a vacancy in the K shell. Then of course K alpha quanta of X-ray is emitted. And if the electron moves from the M shell to fill the vacancy in the K shell, then of course a K beta quanta of X-ray photon is emitted. And if the electron vacancy in the K shell is filled by an electron from the N shell, then of course K gamma is released. That is, an X-ray in the K gamma energy is released. And you see that the transition form also made from the O shell, from the P shell, and so on. And of course, higher orders of K series will be eliminated. Now, if an electron lying in the valence shell, for example, very close to this gray level, when the electron has a very high value of a principal quantum number and is jumping to fill the K valency, K vacancy, K whole vacancy, then you see that electron is jumping from the very far end of the shell to fill the K vacancy. Then of course that quantum of photon will be very high in energy, and that is referred to as the K edge. And that will have an energy corresponding as shown by the black arrow. So this will actually correspond to the energy of the K edge. So if an electron is moving from an n is equal to infinity shell, but still the electron is a part of the atom and is moving to fill the vacancy in the K shell, then of course the quantum of energy that is released will be very, very powerful, and that will give you the K edge photon, K edge quantum of X-rays will be the most powerful photon emitted in the K series, and the corresponding wavelength will be very small. Similarly, you see that I have shown the L spectra, L series, L alpha, L beta, L gamma. L alpha is due to the transition when the electron moves from the M shell to the L shell. L beta is due to the transition for when the electron moves from the N shell to the L shell, and L gamma will be the transition when the electron moves from the O shell to the L shell to fill the vacancy of the to fill the whole vacancy in the L shell. Similarly, M series has been shown. So when the electron moves from the N shell to the M shell to fill the whole vacancy, then of course M alpha is generated. And when the electrons move from the O shell to the M shell to fill the whole vacancy, then of course M beta is generated. And similarly, when the electron moves from the P shell to the to fill the vacancy in the M shell, then of course M gamma is generated. Similarly, you see that ultimately the last most energetic photon that is released in the M series will be the M edge. And the M edge will have an energy equal to the energy shown by this upward arrow, which is the energy required to ionize an electron from the M shell. So you see that the ultimate energy of each series will correspond to the edges. So the K edge, L edge, and M edge will be the quanta of X-ray photons which will have the highest energy of their series. And you know that these series are generated when electrons move from corresponding from higher orbits to the base orbits. For example, for the K shell, the base orbit is n is equal to 1. For the L series, the base level is m is equal to 2. For M series, the base level is m is equal to 3. And the electrons, and when the holes are created by the ionization process, then of course the whole vacancy is filled by the electrons in the surrounding orbits, and the difference of their binding energies will be released as the quanta of X-rays. So ionization of inner electrons in the KLM shells are shown by the thick upward pointing arrows shown in black, in blue, and in red. So these arrows in black, blue, and red. Thick arrows, upward arrows show the ionization of the ionization energy required to move the electrons from the K shell, from the L shell, from the M shell respectively. 3 lines each of K series, L series, and M series are also indicated. Unsplit K, L, M, N, O, P levels corresponding to N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4, N is equal to 5, and so on are shown respectively. So you can see that the K level corresponding to N is equal to 1 is shown. The L level, which is an unsplit level, is shown for N is equal to 2 level. The unsplit M level is shown by a single line M is equal to 3. Similarly, N level is indicated by N level is in N shell is indicated by N is equal to 4. O shell is indicated by N is equal to 5, and so on. So you see that lambda X, that is the X-rays which is emitted, is greater than or equal to, or at least equal to lambda excitation. And this is only the excitation when the excitation is done through optical means. That is, you have a mixture in the gaseous form and you excite that mixture with, for example, a laser light. Different levels can be excited, and that wavelength is called the excitation wavelength. And of course, the other wavelengths that will be emitted will be greater in wavelength compared with the lambda excitation. It is because the energies that will be released will be smaller in energy, and smaller in energy mean that the wavelength will be greater. So lambda X-ray that will be emitted through the optical excitation of such materials, the lambda excitation or the lambda emission, the lambda X emission will be greater than the lambda excitation. So lambda X emission is independent of lambda excitation within a certain limit. Although there are many parameters on which this can depend, but we are not going to discuss those parameters. But under certain conditions, this may be assumed independent. So the lambda x emission will be greater than the lambda excitation, because the energy that is released by the sample will be smaller than the energy it has absorbed. And due to that one, the lambda x emission will be greater than the lambda x excitation, because lambda excitation. The lines of a series appear in a fluorescence spectrum. Fluorescence spectrum means that you excite a sample with X-rays, and you also observe the X-rays emitted by those materials. That is called the fluorescence spectrum. So the lines of the series appear in a fluorescence spectrum all at once when the quantum energy of excitation radiation is greater than the highest energy photon in the spectrum. So you see that if your energy, that is the excitation energy, is very high, for example, corresponding to the O level, then of course the K level, all the transitions will immediately takes place from the L to K, from M to K, from O, from N to K, from O to K, from P to K, and so on. So at once you can observe a spectrum, fluorescence spectrum can be observed immediately. In the characteristic spectrum obtained with bombardment of electrons, the kinetic energy of electron represented by EV0 must be greater than the highest energy photon in the spectrum. So here we are talking about, when we are talking about the fluorescence spectrum, it means that the excitation energy of the exciting photon, for example, a laser beam, should be greater than the highest energy photon in the spectrum. For example, in the spectrum of the K series, or in the spectrum of the L series, or in the spectrum of the M series, the exciting photon must have an energy greater than the highest energy of the photon in the spectrum. And if you are generating X-rays by the bombardment of the highest energy kinetic energy electrons with an energy EV0, then this energy EV0 must be greater than the highest energy photon in the spectrum. To obtain the emission of K alpha line, the input radiation must supply an energy equal to K edge. This is the energy to which the lines of the K series converge the series limit. That is, if you want to obtain the K series limit, not the K alpha line, but the K series limit, that is all lines of the series, what you need to do is that you need to supply an energy which corresponds to the energy for the excitation or for the ionization of electron. If you supply this much energy, then an electron from the K shell is ionized, and immediately you will observe the K alpha line, because the vacancy is generated in the K shell by the ionization process, and immediately the most probability is that an L electron from the L shell will jump to fill the vacancy of the K shell. And of course, the K alpha line will be immediately emitted. So K alpha X-ray will be emitted immediately when you supply an energy to ionize the K shell. And then other lines K beta and K gamma will be released. But immediately K alpha will be released, because this vacancy will be first filled by the electron in the L shell. So to obtain the emission of the K alpha line, the input radiation must supply an energy equal to K edge. This is the energy to which the K lines of the K series converge the series limit. And you know that series limit mean that the highest energy photon from the farmost shell, probably the valence electron, jumps into the K shell To fill the electron vacancy, then of course the highest energy photon will be emitted, which corresponds to the photon of the K series edge. X-ray emission corresponding to the state of the inner electrons is filled with shells. Of course, then you know that other jumps from the L shell, from the M shell, from the N shell, from the O shell, from the P shell, electrons will ultimately jump to K shell to fill the hole vacancy in those shells, and then of course a series of X-ray spectra can be obtained. Optical spectra is related to more loosely bound outer electrons. So you see that when we talk about the X-ray spectra is related with the inner bound electrons and of course highest in energy. Whereas the optical spectra, normally we talk about the optical spectra when we excite, when we do the transitions with valence electrons. That is when the valence electrons is excited or moved to the higher orbits, then the spectrum that we observe is normally referred to as the optical spectra. And it is related to a more loosely bound outer electrons, whereas the X-ray emission spectra is related with the inner bound electrons, strongly bound electrons in the inner shells. Causal in 1916 interpreted the generation of X-ray line spectra as follows. First, the exciting electron must remove an atomic electron from an inner shell. That is, for example, you must remove an electron from the K shell if you want to observe the K series, or if you want to observe the L series, you must remove an electron from the L series. If you want to observe an M series, you must remove an electron from the M shell. So first the exciting electron must remove an atomic electron from an inner shell. Resulting hole is filled by outer electrons and their energy is released in the form of characteristic light quanta, or in the form of a series of quanta, for example, from the K series or from the L series or from the M series. All transitions which end on the same inner shell occur together and form a series. For example, if you have removed an electron from the K shell, then all the transitions from the higher orbits, from the higher shells, will take place to the K shell and a K series is formed. Transitions involving inner shells are much more energetic than those in the outermost shell, because the electrons in the inner shells shield the nuclear charge for the electrons in the outer shells, and being very close to the nucleus are strongly bound with the highest binding energies. That is, the K shell electrons has the highest binding energy in comparison with the other shells. For example, with the electrons in the L shell, electrons in the M shell, electrons in the other shells, etc. A screening of the nuclear charge is by Z-1 for K alpha lines and by Z-7.4 for the L alpha lines. The field strength in the interior of a sphere with a uniformly charged sphere is 0. That is, for example, if the electron is in the K shell, then of course the field at the electron in the K shell due to the electrons present in the other shells, for example in the L shell, in the M shell, in the N shell, etc., then due to those electrons, the field at the electron in the K shell is at the electron in the K shell is 0. So the fields at the inner electrons from the field due to the outer electrons is 0. The inner electrons experience no field due to the outer electrons. So you see that I have, this is the second lecture I have presented, and you know that I have discussed some more greater detailed about the X-rays, their emissions, their series, and how they are emitted, how the vacancies are filled with the electrons from the outer shells, and what are the edges of the K shells, and what are these series, that is the K series, L series, M series, N series, etc., and so on. So the lecture is actually continued, but this is the end of slide number 16B.